Hello and welcome to Honors Function. In this second video on rational function, we're going to go over more examples about limits and graphs and asymptotic behavior of a rational function. Let's start with the first example. So, example 1, we have to find the limits of this rational function right here. As x approaches negative infinity and plus infinity. Well, that is called an end behavior, right? And if it's called an end behavior, this is a bottom heavy. Oh, I know how it behaves. It goes towards 0. So in both cases, the limit is going to be 0. So here, I should have left a little bit of room. This is equal to 0, and this is equal to 0, because it is bottom heavy. Okay? Please do example number 2. I'm going to do example number 3 now. Example number 3. This is the top-heavy rational function. If I wanted the equation of the asymptote, I would have to do a long division. No choice here. I have to divide by negative x squared minus 3x plus 2. I would have to do long division. But the question is not to find the equation of the asymptote. It is to answer the limit question. Therefore, I'm just going to say that x cubed minus x squared plus x plus 5 over negative x squared minus 3x plus 2 is equivalent to, at plus or minus infinity, it's equivalent to what? It's equivalent to x cubed over negative x squared. And that is just negative x. Now, negative x, I know how it goes. It goes something like this, right? Okay, so the limit at negative infinity is going to be plus infinity. Okay, so here, limit as x approaches negative infinity of, let's call that f of x, because I'm lazy, and that's going to be plus infinity, while the limit of f of x at positive infinity is going to be negative infinity. Okay, so you do example 2 and example 4. Let's move on to example 5. Example 5, you have to find the vertical asymptotes. Now we know what's going on for vertical asymptotes of a polynomial function, right? If you have p of x divided by d of x, for vertical asymptotes, you want d of x to be equal to 0, but you want p of x to not be equal to 0. Very important. This function doesn't seem to mean. The first thing I'm going to do is try to factor it. So let me take an x out of the top. 2x squared minus x minus 3 divided by, now this is a sum of two cubes, right? So it's x plus 1 times x squared minus x plus 1, right? Let's continue with the top. X times, so let's try 2x right here. X, I want 1, so I need a 3 here and a 1 there. It's minus 1, so minus 3 plus 2, here we go, minus 3 plus 2, over x plus 1 times x squared minus x plus 1. Now, the solution right here, of course, they have to be real, right? I mean, you are trying to graph something. A complex vertical asymptote doesn't mean anything, okay? So they have to be real. And I know that this one has only complex solution, if you haven't made a mistake. The zeros are complex, okay? So excuse me for the notation right here. I'm talking about the zeros, right? So the denominator has only one real solution, and that is negative 1. Unfortunately, it's also a solution of the numerator. So you do not have any vertical asymptotes. No vertical asymptotes, okay? While the domain here, be careful, the domain is all real number except negative 1, okay? But at negative 1, what you have is a hole in the graph. You can check on your calculator for the graph of this function, okay? You do example number 6. I'm going to do example number 7. How do you like the pace so far? Pretty good, huh? Example number 7. Okay, so whoa, what is going on here? Oh my gosh, look at the top. Degree 4. So I'm not about to factor that, okay? I don't feel like factoring this. I'm not sure I could. And maybe it's not that hard, but I look at that and I'm getting scared. Okay, the question is to find the vertical asymptotes. I can easily answer the question without having to factor it. Now, if I had to graph that, I would have to factor it, right? Because I need to find the x-intercept and stuff like that. But I just want the vertical asymptote. So what I need is a 0 of the denominator. And I know how to factor the denominator, right? So let's see. I think I know. X plus 2, x plus 1. All right, so the denominator has two zeros, -2 and -1. I just got to make sure that they don't make a 0 at the numerator. That's all. So how about we just, check out with a synthetic substitution. So 1, -4, 3, 4, -4. Okay, I'm checking that the 0 of the denominator are not zeros of the numerator. And if they are, you don't have a vertical asymptote. Let's go. 1, -1, -5, 5, 8, -8, -4, 4. Okay, well, at -1, you do not have a vertical asymptote. Gotta check -2 now. Okay, if it's a 0, again, you won't have any vertical asymptote to this function. 1, -4, 3, 4, -4, 1, -2, -6, 12, 15, -30. Forget it. It's gonna multiply by 2 by -2. So that's not 0. Okay, this is not 0 at the end. So you do have a vertical asymptote, and it's just x equals -2. That's it. Okay, so please, you do 6 and you do number 8. Let me do now a problem dealing with a graph of a rational function. So folks, in this case, I'm going to do number 9, and I am going to check tomorrow that everyone has done I'm sorry, there's two number 9s. I'm looking at the thing and it's like number 9. I'm going to do the first number 9 while you're going to do the second number 9, okay? So I'm doing 9-1 and you do 9-2. 9-2 is a little bit more involved than 9-1, and I will check tomorrow that everyone has done 9-2, and I would like everyone to have solved it, okay? All right, study the following rational function. Let's go. I told you how I start. I start by factoring. So f of x equals 2 times, and this is x squared minus 1, so it's x plus 1 times x minus 1 divided by x plus 1. Yes, I know, I'm taking the easy one here, okay? All right, domain. The domain of f is everything except -1. All right, so now that I have my domain, I can do this and this, common factor, common 0. All right, 2. Forget the parity. The top is even, actually. This is an even function right here. But the bottom is neither odd nor even, okay? So it's not going to be any, you won't have any parity here, no symmetry. So we're looking at the x-intercept. So x-intercept, I see it right away. I see it here, right? So it's 1, 0. Y-intercept. For the y-intercept, I'm not looking at the factored form. I'm looking at this right here. Cancel that, 0, -2. Here's my y-intercept. 4, hole in the graph. Yeah, there's a hole in the graph right here at -1 because you can cancel. Hey, what is the coordinate of the hole? Well, let's see. After you cancel, you have 2 times x minus 1. To find the y coordinate of the hole, you just plug in the x coordinate right here, right? So -1 minus 1 is -2 times 2, -4. Okay, I just plug in the coordinate in the simplified form, right? If you plug in the coordinate in the unsimplified form, it's going to give you 0 over 0. That doesn't make sense, okay? So, what do I have? Oh, I need my vertical asymptotes. Vertical asymptotes, I don't have any, right? Because there's nothing that makes the denominator equal to 0 and not the numerator, so no vertical asymptotes. And so now let's graph it. So let's go. Let me graph it here. It's going to be a pretty straightforward one. X-intercept 1, 0, right here. Y-intercept 0, -2, right here. Hole -1, -4, right here. And we know what's going on. This is just 2x minus 2, okay? So this is a disguised form of a line with slope 2 and y-intercept -2. This right here is just a line that has a hole. That's it. It's a line with a hole. Please spend some time doing number 9 second, okay, the second number 9, I want to see some good graphs there, okay? Make sure you don't make any mistake. It may take you a good 10 minutes for this one, all right? Okay, let's finish the whole practice. I'm going to do example number 12, and you're going to have to do number 11 and 13, but we've already worked on these. This is pretty quick. Example 12 now. All right, so without using the calculator, you have to tell me what is f of negative 120, okay? And I don't want the exact value, I want an approximation. So what is f of negative 120? Well, this is a top heavy. I'm going to be using the, actually, let me not write this. Let me just say at plus or minus infinity, f of x is about q of x. Okay, it's about equal to q of x, and that's a quotient. So I need to find my quotient. I really don't mind that because I'm dividing by x minus 4. I can simply do a synthetic, right? It's going to be very quick. I don't care about the negative 6 right here. I'm not going to use it. I divide by x minus 4, so 4. Okay, so 3, 12, 19. Got it. So the quotient is 3x plus 19. So f at negative 120 is about 3 times negative 120 plus 19, and that is negative 360 plus 19, which is negative 341. Okay, that's it. Oh, percent error. Okay, let's do that very quickly. Okay, so folks, look at that. In y1, I have my exact function, my function, right? In y2, I have the asymptote at plus or minus infinity, and in y3, I have almost the percent error. I forgot to multiply by 100. So let's multiply this by 100 just to have a percent, right? Right now, if I don't multiply by 100, it's just out of 1. So here we go, out of 100. And let's check out the table. So I got to make sure my table is on the ask mode. I am on ask, great. So let me check on my table. And I want to find at negative 120. So I'm entering negative 120. Enter. And the percent error is 0.16%. That's not bad. Actually, here, look at these numbers right here. At 50, the percent error is less than 1%. Even at 50, it's less than 1%. Here, at 5 is kind of big, right? It's 67%. Of course, at 5, this is not an end behavior right here. But let's check out at 10. Let's check out at 10. At 10, what do we have? 19%. Okay, let's check out 20. At 20, what do we have at 20? 5% at 20. So where is it becoming less than 1%? That could be a question I could ask you on a test with calculator, okay? What is the first integer where it's less than 1%? Well, in this case, okay, you go to the table right here and you stop doing the ask and you go on auto, and then you check out the table right here and you just go down the table until you see 1% in that column right here, okay? All right, I'm gonna stop it right here. Thank you for watching.